I think kind of in the very early 40s, possibly late 30s. Bell and Howell made a series of very successful combination film projector amplifiers, which also had kind of a set speaker, and you could roll these out on a cart and set everything up, and they're kind of all in one kind of gadgets. And inside the film projector was the sound amplifier, which took the signal from a light shine through the little side of the film, and then converted that with a photocell into a sound signal that was obviously then amplified. There's a lot of different amplifier parts that went into a single model of projector, and I think obviously with all the complexity of the optics and the mechanics of the projector models didn't change that much, but Bell and Howell successively modified the amplifier bit that went into the chassis, or it went into the projectors themselves. So the Model 156 projector, for example, had at least 4 different, possibly 5 different amplifiers that could have gone into a Model 156. And easiest way of finding out what your exact model is to look under the part number here. And here, this is part number 13817. And there are even modifications between certain serial numbers of the different parts. So if the reason I'm kind of going over this and harping on a little bit is if your goal is just to do a minimally invasive kind of conversion where you can take the projector amplifier and make a guitar amplifier without changing a whole lot, you do need to be aware of the individual circuit changes, because there were a number of them. And it's not safe to assume that just because you have a Model 179, it's going to be one particular schematic for all of those Model 179 projectors. So in the early days, there was the Model 156 projector, which had part numbers 12814, 12815, 13728, and 13817, and then at the very end of the projector model run, they had some of the early versions of the 14027. And then with the Model 179 projector, the most common model, or the most common amplifier, I think that was one of their more successful ones, was the 14027, of which there's a couple of varieties. Noise is an issue, and hum with pretty much all of the FilmoSounds is the stock. I think just following and looking at all the different schematics for all these different models over the years, that Bell and Howell successfully tried to mitigate some of the hum and noise issues associated, or commonly associated, with the design. Now, having said that, it is possible, if you got one of these chassis and just used the transformers, to get an amplifier that is extremely quiet. But there's a couple little tips which I'll go into during the build stage, which are going to be the key to getting a quiet amplifier. I think one of the downsides, the physical constraints of the chassis are extremely tight. The transformers are close together right near the rectifier, power tubes, and preamp tubes. The other thing that could be an issue in the design itself is these old octal amplifiers typically used a pentode first stage for amplification. And not only is a pentode kind of tends to be a little bit on the noisy side, but the grid connection here, which is this little top hat thing that goes there, also did not use shielded cable. So the other thing I want to mention very quickly is that before you actually start getting into one of these, and it's a non-trivial task, if you're going to just try to replace old capacitors and not do a whole lot else, there's these banks of electrolytic capacitors here, which were the reservoir and filter caps, but there is another whole bank of capacitors that lies under this circuit board, or The original capacitors that are in there just vary tremendously. I think depending on what they had available, you'll find, old bumblebees, you'll find some black beauties, you'll find a lot of these kind of rectangular solar paper and oils. There were Olmencos, there were, all different kinds of capacitors. Some of them are still usable, the silver mica ones in particular. But the other thing that tends to go bad are the pots themselves. It does amaze me, just to think about the assembly line back in the day in the 40s. And, the wiring is actually incredibly meticulous. It's incredibly dense. And so the quality control and the technical skills of the folks that put this together, just kind of blows my mind. Having said that, I think most people, basically feel that it's less work actually to do a gut job and to put a different amplifier design in, or you can recreate the original design just without all the extra bits. Kind of the tone stack's a little bit goofy, and the feedback is kind of goofy in the design. But I'll go into that later. One thing also that you really want to do before you actually start getting into any of this in either a gut job, which it takes a good 3 hours to clean one of these things out really nice, or if you're just going to try to do a minimally invasive reconstruction, is you do want to test the transformers. And you can test the transformers, completely in situ. I have had several of these where, the power transformers tend to be good, but the output transformers, I had several that had bad output transformers. If you do have a bad output transformer, you can simply use something that's in the 15 watt range that gives you about 8.3K on the 8 ohm as a primary impedance. This one here is actually the model that succeeded the model, I think 285, I'm guessing. It's a little bit later. This is probably mid-50s. And this is a model 620, which is the same as a 620 or 601. So all of these are all octals that, good for conversion. There's some cool design features. Trying to figure out why Bell and Howell recessed the 5Y3 socket. And closest thing I can figure is this is the hottest tube that you're going to have. It's runs hotter than your 6V6s. And my guess is they recessed this to kind of dissipate heat. And I'm also guessing that they put the power transformer here in very close proximity because the power transformer probably acted as a heat sink for the rectifier. And these in the projector are completely enclosed, so there's not a whole lot of ventilation to begin with. So that also obviously affects the condition of your wiring. So you do want to check your transformers are good. The other cool thing is the pentode input octal tube socket is suspended, and my guess is that's probably to mitigate some of the microphonic issues that are inherent in having a high gain first stage of preamplification. So this is kind of the more famous Model 385. These are actually, unfortunately, super hard to come by now, I guess because they're so popular as a conversion. But these have two 12AX7s, phase inverter and input stages, and then also the same complement of 6V6s for the oscillator power section and a 5Y3. The model 601 actually has a different rectifier 5Z4, and you do have to be careful because some of these old, even some of these in-between models, you may have a 5Z4. So the main caution I want, I guess, to convey is you'll see a lot of Model 185s out there. And the Model 185, or the part number here is 05311. These are not great for simple guitar conversion. I'm paraphrasing in the service manual that goes over all these different models, but they said for this part number that went into the 185 projector, they were trying to cut down the weight. So what they did was they completely got rid of the power transformer and actually went into a voltage doubler. And this decreased the available output power of the amplifier from 12 to 15 watts down to 10 watts. But with the voltage doubler, you're also going to get a lot less headroom. And the other thing is they use 25L6 power tubes, which, as the name suggests, use 25 volts for the filament heating. And then the other thing is the output transformer typically is about half the primary impedance of the older models. So even though these are, super easy to find and they're dime a dozen, I think you got your work cut out for you if you want to actually convert this into a guitar amplifier. Maybe you can use the chassis, but most of the other parts are not really going to be usable. So on these old octal chassis, there's a whole mess of stuff you can do. From a build standpoint, a lot of people do kind of variations of the 5C3, the old octal Tweed Deluxe. But you can also do some of the old Gibson designs, which included a pentode preamp. I just wanted to show you 3 chassis here. These are all 14027s from kind of later model 179 film projectors. And this one actually is pretty much stock conversion to a guitar amp of the original Bell and Howell circuit. And what I did was I took the original circuit diagram and removed all the stuff that was not associated with amplification. And this also had a bad output transformer. So what I did here was just, there's, great and readily available replacement output transformers in the 12 to 15 watt range. And you're kind of looking for something that's kind of in the 8.3 to 8.5K range for most of your 6v6 power tubes. But this amp is pretty simple. Just basically recreated the relevant bits, so to speak, of the original design. You can utilize all of your octal tube sockets, and this design I did was it's an original design, and basically instead of kind of the top hat grid 6J7 substituted a different tube, 5691, but using kind of all the octal sockets here. So 2 6v6s, a couple of 6 SL7s, a 5Y3, and here's an earlier model chassis that is, and again, original design, but I'm not using this tube socket. So pretty much the sky's the limit. There's lots of fun involved in kind of designing your own stuff, especially if you're a fan of kind of the old octal tube sounds. So this is what the inside of the film projector chassis looks like stock. And the circuitry turns out is not really all that applicable to a guitar amplifier. If you just basically refurbish the film projector amp and then plug a guitar into it, it works, but it's super gainy and it just doesn't have a whole lot of mojo. And without going into all the design details why, what I like to do is just keep the chassis for the chassis itself, but also for the irreplaceable transformers, which are the power transformer and the output transformer. So what I'll do is I'll skeletonize all of the stuff here, essentially gutting the chassis. And this is what it looks like after I've taken all the bits out. And then once I've gotten the transformer leads isolated, we'll dress those up. And then I do a thorough transformer evaluation for both the output transformer as well as the power transformer to see exactly what voltages are being made. They will be a little bit different, even, and I've noticed even within the same general serial number of chassis that there are some differences. So what I do is I measure the transformers very meticulously, and then I tailor the circuits so that they're optimized with regards to my design parameters and the load lines and the tubes that we're planning on using. And over time, you end up collecting a lot of old stuff. Some of this is actually kind of cool, but there's value in some of these old paper and oil capacitors from back in the day, and there's some cool silver mica capacitors which can still be used, even though I don't. From all of the pull parts, there are certain things that typically can be reused, and I like to reuse them. The original switches, they don't make switches like this anymore. They're super high quality American stuff. But what I end up doing is deoxit, spray some deoxit in there and rejuvenate and refurbish these switches, and they just work phenomenal. The other cool thing is the original fuse holders, and if they're in good shape, I'll be able to reuse those, and the knobs. They do make knobs like this now. There's a company, I think it's Davies maybe or something like that, that makes really high quality knobs that look just like this, but I just think it's super cool if you got something that's 80 years old to use that. So at this point, after a few hours of painstaking work, we've got pretty much the chassis gutted, and we've got all the individual lugs of the tube sockets that we're going to use. Those have all the old connections have been removed and the solder cleaned up. I keep the original plate connections to the output transformer, and the original wiring coming out of the transformers, even though I've checked the transformers and they're a-okay, they're totally up to original specifications, the lacquer coated wiring over 80 years of being exposed to heat and who knows what other abuse, some of that insulation is a little bit sketchy. So what I've taken is heat shrink tubing over any sketchy areas of the original power transformer wiring, and we've actually put in backup rectifier diodes here, so these will actually be already rectified before they get to the rectifier tube here, and that just performs the duty of an additional backup step in case of rectifier tube failure. What you see here is our 6.3 volt wiring, and I've actually wired up the heater filaments for our two 6V6 power tubes here, and also our third stage again into our cathodiene phase inverter, which is a 6SL7, and wiring for the 6.3 volt filaments for the first two stages of preamplification, which is a 6SL7. Then you notice these the 6.3 volt filament wires are really tightly wound. This is to prevent any noise, AC noise, from these 6.3 volt filaments getting into areas that we don't like. Now, because this is such a compact chassis, and they're actually known for being noisy, so what we're trying to take is every step we can to minimize any extraneous noise. And what we've also done is substituted a multi-component capacitor can for the original bank of capacitors. There was, and these are the 5 volt heaters that go to the rectifier tube, and the second of which is connected to the cathode of the rectifier tube, which is where our high voltage DC is going to be coming out. We've hooked up our multi-component can capacitor here, and we've installed the IEC, so current safety standard 3-prong plug. We were able to salvage the original fuse holder, which was in great shape, and we're also able to refurbish and save the original power switch, which is also in great condition. So what we've done today is we've connected some protection circuitry into our power section. And what this is a thermal cutoff mated to a metal oxide varistor or a TMOV. And so what this will do is it'll sacrifice itself in response to sudden voltage or current spikes, and give enough time then for your slow blow fuse, if there's a persistent fault situation, for the slow blow fuse to actually melt. The other thing we've done here is I've added what's called a negative temperature thermistor, or an NTC thermistor. And what this does is act as a inrush current limiter. So when this device is actually cold, it has a significant amount of resistance in the several hundred ohms category. And as it heats up, that resistance actually drops to zero. So in an initial cold situation where you fire your amp up, there's this big surge of current inrush that goes to starting to heat up the filaments of all your tubes. And what you don't want for tubes, which is hard for tubes, is if the filaments are just heating up and then they're exposed to a large voltage differential between the plate and the cathode. So what you want is to give the tubes time to actually get their filaments fully heated up before that high voltage is applied, that high voltage potential between the plate and the cathode. And that's what this little inrush current limiter helps to do. We've completed our wiring for our reservoir capacitors as well as our filter capacitors, and I've also included a circuit here which provides steady DC base voltage to the AC of the 6.3 volt filaments. And as I mentioned before, these chassis, because they're so compact, they're subject to being noisy. So taking all these additional steps brings that noise floor down as far as humanly possible. And that's what one of the goals of not only tight heater wiring, but also putting a DC current floor on the 6.3 volt filaments. Another day's work sees our power tube wiring nearly complete with grid reference resistors, grid stoppers, and under here you can see our screen grid stoppers. Grounding scheme is now complete. We've installed our Teflon military surplus Russian high-performance coupling capacitors, which will ultimately take our signal from our phase inverter to the power tubes. And we've also assembled our tone stack. And that's where we're at right now. What we'll start doing now is kind of the latter phase of construction, which will involve wiring up our preamp stages, and then also our third gain stage and phase inverter before connecting up our connections to the volume and tone pot and switches. We're able to do in the next stage, wired up the volume and gain boost circuitry, which just pops out here. We wired up tone stack. We wired up phase inverter and third stage of the preamp. We wired up connections from the phase inverter to the power tubes. We connected up our input jack. We connected up our first two stages of gain here, and we also made all the connections for the tone pot here, and this is actually pops out here. And so pretty much all we have left to do is wire our output jacks and wire our indicator light. So the amp is now complete and fully tested. All our voltages check out great. They're only within a couple, 3 volts of what was predicted with our SPICE models. And one thing we did spend a fair bit of time on was choosing the appropriate cathode bias for our cathodiene fed 6V6s. These are the output tubes. And like with fixed bias, you typically run somewhere around the 70% of maximum wattage for the power tubes. But with cathode bias, you could actually run that a little bit warmer. I think the safety range is somewhere between 70 and 85% is what most people use. However, that range gives you a tremendous amount of difference in both gain as well as feel when you're playing it. So somewhere between that range is usually a happy spot, and that with every single amp takes a little bit of fiddling around, especially because these old power transformers and the old output transformers will vary somewhat. When you're working on especially a very compact chassis, or you're doing a higher gain amp design, kind of minimizing noise and hum are one of your key design and construction goals. And I just thought I'd give you a few little kind of tips from experience on how you can reduce hum and noise in an amplifier, any amplifier, whether you're building a complex or really compact design like this, or a turret board or whatever. And one of the things is to avoid hum loops, and those are basically when you have heater wires that are coming around your chassis, your tube socket. You want to avoid kind of running AC heater wires in parallel, and you want to try to twist them as tightly as you can. I like twisting them by hand. A lot of people use a kind of a hand drill and kind of run them through that, chuck to something. Problem with that is sometimes you can over tighten them and you can damage the insulation on those, and these old, at least the cloth wax insulated kind of vintage wires, super easy to twist by hand. So you want to make sure your twists are tight. You want to route your heater filaments or heater wires away from anything that's sensitive that could pick up an AC hum, for example, especially kind of your grid circuits. And the other thing you can do is you can DC elevate the AC that this circuit is on. The quick and dirty way is just to ground the center tap of the heater filament to the cathode, if you're using a common cathode biased power section, depending on what power tubes you're using. For example, 6v6, you're probably going to be somewhere ending up with a DC lift of around 29 to 32, somewhere around there, volts. Or you can, as in this design, dedicate a voltage divider from your DCB plus to give you a clean source of DC to elevate your heater circuit. The other really important thing is to observe proper grounding procedures, and there's just tons and tons written about grounding schemes. But to make it simple, if you just think about grounding everything that's in your preamp side to what's called a star ground, or where it all comes together, and make sure all of this stuff is grounded close to your input jack. And that would, of course, include the grounding for the input jack, your potentiometers, your tone circuit, and the cathodes of your preamp tubes. And then also separately ground all your power supply stuff. The center taps of your power transformers, the capacitors that you use for filtering, as well as your reservoir caps, and also the cathode, if you're doing a cathode grounding scheme for your power tubes. So in this design, basically, I have a star ground here for all my preamp stuff, and I have a star ground here for all of my power stuff. The other thing is you want to have a dedicated ground from a safety standpoint for your ground of your three-prong power coming in. Be conscious of your lead dress, and that's important for anything, obviously, but on your preamp tubes, make sure your lead dress kind of avoids coming into contact or in proximity to noisy AC stuff. Another trick is to use shielded cable for all of your preamp tube grid connections. I was mentioning reverb and tremolo. Those can be super duper noisy. So if you have a reverb or tremolo amp, you're going to want to be conscious of how you route the leads going to that section of the circuit. Not often talked about tip is also when you look at all the capacitors in your circuit, whether they're on the tone circuit side, whether they're coupling capacitors, not so much your bypass capacitors, but on the signal side of things, the majority of your capacitors will have a foil end and they'll have a non-foil end. And you want to make sure that the foil end of your capacitors kind of goes towards the lowest impedance side of whatever circuit they're in. And I've seen a lot of people build, really pretty amps, but they don't pay attention to the kind of the foil end or the non-foil end of the capacitors. So even though the capacitor is all lined up and all the writing is the exact same way, they're not necessarily quiet amps because of this simple thing. So sacrifice pretty for quiet is good. Make sure, obviously, all your solder joints, because that's another common problem. Whether you're routing to turrets, an eyelet board, or actually something like this where it's point to point, make sure there's a good physical connection before you actually apply solder, and then make sure your solder technique is good so you avoid cold solder joints. And those are kind of the nitty-gritty kind of experience-based tips that can actually really change an amp from a noisy, hummy, hissy one to one that's actually as quiet as you can make it. So now the amp's complete. Your voltage tested everything. Everything looks good. Kind of want to know, was all that forethought with regards to efforts to mitigate hum and noise, did it all pan out? And if you follow those tips that I gave you, even with a super crowded amp like this, it can be really quiet. So we've got the amp up, and I mean, this is how much noise we have. I mean, we've got fluorescents all over the place, which are super noisy, or LEDs actually. And the background noise floors is incredibly quiet. And that's with the guitar plugged in. Then we can kind of test our stuff and then make sure we're all happy with it. What we want to do now is, ideally, you want to be able to kind of look at what the heat distribution is for your chassis. And we know right off the bat that there's going to be some hot spots. And we just want to make sure that we've constructed our amplifier so that hottest things like this rectifier tube, which will easily get over 300 C or 300 degrees Fahrenheit, notice how it's in close proximity to the power transformer. And again, I think that's because they designed the power transformer to act like a heat sink to pull heat off of the rectifier and dissipate it. The other hot things in this amp are going to be your power tubes, about 200 degrees Fahrenheit. And I like to think of a cool side of the chassis, which is the preamp side. The preamp tubes usually only get to maybe about 100 degrees Fahrenheit. And all our more sensitive, temperature sensitive passive components should be on the preamp side. So if we flip the chassis over, we do expect to see some hot spots. For example, something that'll get hot on the other side is your common cathode bias resistor for your power tubes. But other than that, nothing should be smoking hot. If you're using voltage dropping Zeners, they can get hot too. But just be cognizant of what's where and keep your temperature sensitive stuff away from the hot stuff, and I think you'll be good. Make sure your amp is well ventilated. A good time with your conversion, and I hope this has been helpful. Good building.